In 2008, two men walked into a federal courthouse in Hawaii and filed a lawsuit against the most expensive science experiment in human history. They weren't crackpots. They weren't conspiracy theorists. One of them had a background in nuclear safety. Their argument was simple. If scientists in Switzerland turned on a machine buried 300 feet underground, it might create a black hole, and that black hole might eat the Earth. The scientists said that was impossible. But here's the part that should make you pause. They were arguing about the same physics. So who was right? And more importantly, what does it tell us about the universe that the question was even worth asking? The machine at the center of all this is called the Large Hadron Collider, the LHC. And it sits in a circular tunnel 27 kilometers long, straddling the border of Switzerland and France. It is, by most measures, the most complex machine ever built by human beings. The lawsuits, there were actually two, one in Hawaii, one in Europe, argued that turning it on violated a duty to protect human life. The plaintiffs wanted an injunction. They wanted the power to stay off. Courts dismissed both cases. The LHC turned on. The Earth did not end. But before you dismiss the plaintiffs entirely, I want you to sit with something uncomfortable. The theoretical possibility they were worried about, microscopic black holes forming inside a particle collider, was not invented by fearful laypeople. It came from physics journals, written by physicists, about real predictions of real theories. To understand why, you need to understand what the LHC actually does. Imagine taking a proton, one of the tiny particles in the nucleus of every atom in your body, and accelerating it around a circular track. Then imagine doing that so many times that it reaches 99.9999991% the speed of light. Then imagine doing that with two beams of protons going in opposite directions and smashing them into each other head-on. That is, in essence, what the LHC does. Billions of collisions per second, each one briefly recreating conditions that haven't existed in the universe since fractions of a second after the Big Bang. The energy released in each collision is tiny by everyday standards, about equivalent to a flying mosquito, but concentrate that energy into a space smaller than a proton, and you are briefly operating at a scale where the fundamental structure of reality starts to crack open. Physicists use the debris from those collisions like a microscope. What particles emerge? How do they behave? What does that tell us about the rules that govern everything? In 2012, that approach paid off. The LHC confirmed the existence of the Higgs boson, the particle responsible for giving matter its mass. It was one of the greatest scientific discoveries of the century. But the Higgs was only one of the things scientists were looking for. There was something else, something weirder. And this is where the lawsuit starts to make more sense. Here is one of the deepest unsolved mysteries in all of physics. Gravity is absurdly, embarrassingly, inexplicably weak. Think about it. A tiny refrigerator magnet can hold a piece of paper against the pull of an entire planet. That magnet is using electromagnetic force to defeat Earth's gravitational pull. Electromagnetism is roughly 10 to the power of 36 times stronger than gravity. That's a 1, followed by 36 zeros. No one knows why. This is called the hierarchy problem, and it is one of the most embarrassing gaps in our understanding of the universe. In the late 1990s, a group of physicists proposed a radical answer. What if gravity only seems weak to us because most of it is leaking into dimensions we can't see? This idea, known formally as the ADD model, after the physicists Arkani Hamed, Dimopoulos, and Diwali, suggests that our three-dimensional world is like a thin membrane floating in a higher dimensional space. Gravity, unlike the other forces, bleeds out into those extra dimensions. We only feel the fraction that stays in our membrane. That's why it seems weak. The prediction of this model that caused scientists, and eventually the plaintiffs, to take notice. If extra dimensions exist at the right scale, the LHC might be powerful enough to create microscopic black holes. Not metaphorical black holes, actual regions of space-time where gravity has collapsed on itself. Just very, very small ones. This is the moment where the story forks. The plaintiffs read microscopic black holes and saw catastrophe. The physicists read microscopic black holes and saw a measurement opportunity. Why such a different reaction to the same words? First, scale. These hypothetical black holes would not be the stellar mass monsters that devour galaxies in science fiction. They would be incomprehensibly tiny, with masses on the order of a few proton masses. Less than a grain of salt by a factor so large, it defies intuition. Second, Hawking radiation. In 1974, Stephen Hawking calculated that black holes aren't truly black. They slowly emit energy and particles due to quantum effects near their event horizon. The smaller the black hole, the faster it evaporates. A microscopic black hole formed at the LHC would evaporate in a time so short, far less than a trillionth of a second, that it would disappear before it could interact with anything at all. But here's the most devastating argument against the doomsday scenario. And it's not a calculation, it's an observation. Earth is constantly being bombarded by cosmic rays. These are particles, protons mostly, streaming in from distant supernovas, neutron stars, and active galactic nuclei. Some of them arrive with energies millions of times greater than anything the LHC can produce. They have been smashing into Earth, the moon, and other celestial bodies for billions of years. If high-energy collisions could create dangerous black holes, the moon would have been consumed long ago. Every neutron star in the galaxy being hit by cosmic rays at energies that dwarf the LHC would have been annihilated. They haven't been. They're still there. That's your safety record, written in astronomical time. The universe has been running this experiment for 13.8 billion years. We're still here to ask the question. The LHC ran for years searching for evidence of microscopic black holes. It searched for signatures of extra dimensions, unexpected patterns in collision debris, missing energy that might indicate particles escaping into a higher dimensional bulk. It found none of it. No black holes, no extra dimensions, no signal of the ADD model. This might sound like failure. It isn't. This is exactly how science works. You propose a theory, you build a test, you look. If you don't find what you predicted, you learn something. The ADD model, at least in the parameter range the LHC could probe, appears to be incorrect, or at least insufficient. The hierarchy problem is still open. The mystery of gravity's weakness is still unsolved. And that is genuinely one of the most exciting sentences in modern physics, because it means the answer is still out there. A deeper theory, something beyond our current standard model, something that explains gravity at the quantum level, almost certainly exists. We just haven't found it yet. The LHC is scheduled to run in upgraded form through at least the 2030s. Proposals exist for even larger colliders, machines that would make the LHC look like a prototype. Every collision is a message from the fundamental layer of reality. We're still learning to read it. In 2008, two men were afraid of what we might find. What we found instead was a new frontier of not knowing, which, if you love physics the way I do, is the most thrilling thing of all. Here's what I keep coming back to. A machine buried under the Alps, built by thousands of engineers and scientists from over 100 countries, accelerating matter to within a hair's breadth of the speed of light. And the biggest discovery it might make is that the universe has more dimensions than we can see. We might be living on the surface of a bubble. Gravity might be leaking. The rules of reality might have footnotes we haven't read yet. If that doesn't make you want to know what's next, I'm not sure what will. Now I want to hear from you. Drop a comment below. Do you think the plaintiffs were completely wrong? Or do you think there's something admirable about asking, but what if, before we flip the switch on something we don't fully understand? I read every comment, and I genuinely want to know where you land on this. And if you're new here, this channel is built around one idea, that the most mind-bending stories in existence are the true ones. Subscribe so you don't miss the next one. It's free, it helps more than you'd think, and it means the world to this channel. I'll see you in the next video.